All right, this lesson is our first review covering a wide variety of topics from this data analysis unit. We have a test coming up, so this is a review, our first review. Before we get to problem number one, a review of this basic sampling vocabulary. Remember, we learned about 6 different types of sampling, six different ways of collecting data. The first 2 here are automatically biased by their very nature. Voluntary sample is when the sample chooses itself. For example, if you post a survey on a website or mail out a survey or set up a table and invite people to stop by and fill out your survey. Voluntary. And then there's convenience. That's just doing the easy thing, walk into a room, survey whoever you see, get on a bus, survey everybody on the bus just because they're there. Convenient sampling. That's by its nature biasing. And then the other 4, simple random, where everyone has a chance to be in it and they're chosen by a random number generator or something like that. Systematic, when you're picking like every other person or every third person or every 5th person, something like that. Stratified random, that's when there are groups, but you take a few from each group. That's stratified random. Okay, like if my groups were freshmen, sophomores, juniors, and seniors, and I picked 50 freshmen, 50 sophomores, 50 juniors, and 50 seniors. All right, even though I'm picking those 50 at random, except for making sure I have 50 of each. That's stratified. And then finally, there's cluster. All right, that's when I'm picking whole groups at a time. Not just a few of each group, but whole groups. For example, if I went through the school and I picked 10 classrooms to survey, 10 whole classes, I would pick those classes at random. So I would still have that, but it would be a cluster if instead of picking, let's say, 5 kids from each class, I picked 5 whole classes. All right, so that's a review of the sampling methods. Now, looking at problem number 1, a person that does not want to go out of his or her way to collect the data to conduct the survey will probably choose the easiest route. What type of sampling will this person use? That's convenience. If you volunteer, participate in a survey, then what type of sample would this be? Well, the word volunteer being right there kind of gives it away. Voluntary. All right, give an example of a systematic biased sample. Now, systematic is not automatically biased, so I'm going to have to add in something extra to make it biased. So first of all, the systematic part, let's see, let me make this font a little smaller. Systematic is when you're picking like every 5th person or something like that. So number the population. Well, let me come up with a story here. Here we go. I want to find out if Roswell High School students like the school lunches. So I ask every 10th person who comes through the lunch line whether or not they like school lunch. This would be systematic because I'm doing every 10th person, but it would be biased because I'm only asking students who are eating school lunches. They're coming through the lunch line. I'm not asking all the people who brought their own lunch from home. And if I did, I might find out that a lot of those kids are bringing a bag lunch because they don't like school lunches. And I might find out that a greater percentage of kids that are eating school lunches don't mind them. Okay? I mean, some kids don't have a lot of choice in the matter, but to the extent that you do have a choice, if you really hate school lunch, you're probably going to be more likely to bring lunch from home. Okay? So that would be biased. So moving on, number 4. The teacher selects students randomly from an alphabetical list and asks the selected students how many hours they study for the quiz. Determine the type of sample and if it is biased or not. Alright, from the information provided here, I got to go with simple random. Alright, number 5. In a survey of 650 students, 27% of the students said they like math. Find the margin of error and find the likely interval that contains all the students who like math. First of all, margin of error. Margin of error has a formula to it. Okay, the margin of error, I will call it MO for margin of error, is 1 over the square root of the sample size. Okay, so in this case, that's going to be 1 over the square root of 650. All right, please understand the sample size is everybody who participated in the survey. All right, so let's go ahead and do this. So 1 over the square root of 650. Okay, so I get this decimal. All right, 0.0392. So moving that decimal over, that is 3.9%. We'll do the nearest tenth. Okay, so that is the margin of error. Now, as far as the interval, all right, I'm going to do that interval over here. Now, 27% of the students in the sample said they like math. Now, if I want to know about all students, not just the ones in the survey, I'm going to have to start with that 27% as sort of a middle number, and then I'm going to do plus or minus my margin of error. Okay, and that's going to give me my likely interval. So, okay, if I do 27 minus 3.9, okay, that's 23.1. And if I do 27 plus 3.9, that's going to be 30.9. Okay, genius. Okay, there's my margin of error. There's my likely interval. Okay, so moving on, number 6. Using number 23 above, how many people of the 650 surveyed actually like math? Okay, well, they said 27% of the students like math. Okay, so 27% of 650 is the same thing as 0.27 times 650. Okay, just turn it back into a decimal and multiply. All right. Okay, so that's 175.5. You can't really have half of a person. All right, so I'm going to round to 176. All right, number 7. If the margin of error is plus or minus 4.6%, then find the sample size. Well, the sample size is the n in this formula right here. So we're trying to solve for n, which means we don't know what n is, so don't go plugging anything in for n. All right, so that means 1 over the square root of n. You know what? Let me zoom in. Bam! Oh, shucks. It's on now. I just went crazy, you guys. Okay, so 1 over the square root of the sample size should equal this margin of error they got for us. I lost it. 4.6%. Okay, I'm going to write that 4.6% as a decimal. All right, so if I convert this back to a decimal, this would be 0.046. So this is the equation. Okay, the margin of error equals 0.046. I just have to solve this for n. Now just do the reciprocal of both sides, okay? Understand that this is like having 0.046 over 1. So I'm simply going to do the reciprocal, okay, in both places. If I do that, then I wind up with the square root of n over 1, which I don't need the 1 under it. And then over here, I'm going to wind up with 1 over 0.046. To find n, I need to get rid of the radical. And to do that, I will square both sides. So 1 over 0.046 squared. That's what we're doing right now. Okay, 472.5, we'll round that to 473. All right, sample size. We're talking about people or whatever, so the sample size can't be a decimal. So round to the nearest whole number. Okay, looking at number 8. What is the margin of error? Oh, wait, what? Okay, I'm lost. Okay, I think suddenly number 8 is supposed to be referring to this chart over here. All right, I'm noticing number 9 and number 10 are all for the chart. Maybe we should have had a line or something. Anyway, what is the margin of error of this data on the chart is what it should have said. So of course you know that the margin of error is the square root of the sample size. So the sample size here is going to be the total number of all the kids in the survey. So if you sit here and add up 45, 53, 99, 44, 66, 22, 37, that's going to be your sample size. All right, so margin of error, 1 over the square root of the sample size. In this case, the sample size is 366. So 1 over the square root of 366, right, which is what I got by adding up all of these numbers right here. Anyway, put that in the old calculator. Okay, so that's 0.052. All right, so that's 5.2%. Okay, so that's our margin of error for this survey data, students' favorite after-school activities. All right, now, what's the percentage of students that play sports? Okay. Well, 45 students in the survey play sports. Okay, now in fact they should have been specific and said what percentage of students in the survey students surveyed. Okay, because we really got to differentiate between the percentage of students in the survey and the percentage of students in the whole population. So anyway, to calculate that percentage, you take the number of kids who play sports and divide by the total. So that's 45 out of 366 kids surveyed. Okay, so it's 45 divided by 366. That gives you 0.123, which is 12.3%. So that's the percentage of students surveyed that play sports. Now, give an interval that's likely to contain the percent of students who like to visit friends. Man, these questions are not worded very well. Based on this, I don't know if we're talking about the, they're saying the interval, so we must be talking about the population, but they didn't say that. Anyway, give the interval that's likely to contain the percentage of students in the population who like to visit friends. Who like to visit friends. Yeah, so in order to answer this question, we need that percent first, okay, like we did for number 9. So first we need to know the percent in the sample. So it's kind of a two-step process. So first we have to find the sample percent. Okay, so how many people like to visit with friends? 99. Okay, so that was 99 people out of a total of 366. Okay, so my sample percent, all right, if I do 99 divided by 366, all right, so that's 27.0, all right? So that's 27.0%. Okay, so that's the sample percentage of people who like to visit with friends. Now, if I want the percent of the population, the interval, okay, and you really only do an interval for a population, so that's how I knew to put this word in here. I have to start with the sample percent, and so I start with this 27.0, and I add and subtract the margin of error. Okay, the margin of error is our 5.2%. Okay, so here we go. 27 minus 5.2 is 21.8%. And 27 plus 5.2. That's 32.2%. All right, so this is the interval that's likely to contain the exact percentage of the population who like to visit friends. All right, let's move on to number 11. Suppose the faculty of a statistics department at a large university wanted to look at how students in the introductory statistics course might perform on exams under different environmental conditions. They decided to consider the effect of the size of the classroom, or a smaller classroom where there are just enough seats for the students versus a large classroom where the students can spread out with an empty seat between each student. When the next exam is given, in one section of the introductory statistics course, 60 students will be randomly assigned to one of the treatments. The scores on the exam will then be compared. Okay, so first of all, is this study an experiment or observational study? All right, well, this is definitely going to be an experiment because 60 students will be randomly assigned. Okay, there's like a key word right there. They're being assigned to one of the treatments or the other. All right, they weren't just already doing it, they're being assigned. So because the condition is being imposed on them, assigned to them, then that makes it an experiment. Okay, the explanatory variable and the response variable. This is like the potential cause and the potential result. Okay? All right, so the explanatory variable is basically going to be the treatments when you're talking about an experiment. Okay, so the two treatments are it's the size of the classroom that they're adjusting. Okay, so I'm just going to put classroom size. Okay, so here we're putting the general category. The difference between this and treatments are when we say what are the treatments, we're going to break it down and say that the two types. But here they're looking for the general, the overall label of what we're doing. So classroom size. All right, name the response variable. So what are we going to see? The scores. That's the response variable. Exam scores. Okay, so those exam scores are resulting theoretically from the classroom size. At least that's what we're experimenting. Okay, that's what we're measuring. So let's see, how many treatments will this study compare? Name the treatments. Well, there are two. And they are the large classroom and a small classroom. Okay. Kabam! All right, so there's your completely randomized design for this study. Your 60 students randomly assigned into two groups, 30 students each, which are then the groups are randomly assigned which kind of room they're going to get, small or big. And then, of course, we compare exam scores. All right, because that's what it said we were targeting. All right, last one, number 12. Outline a completely randomized design for this one. Fluoride is often put into drinking water to help keep teeth strong in young children. To study how the bodies of young children process calcium, investigators used the setting of a summer camp. Fluoride was given in Hawaiian Punch at either a high or low level. The camp diet was otherwise the same for all children. Suppose that there are 200 campers. Completely randomized design. Well, yeah, I'm just going to cut and paste this, okay, to build my completely randomized design. Okay, I'm just going to change the numbers. Okay, so instead of 60, it's 200. I guess instead of students, I should say campers. No. All right, so 200. You know, I'm going to do this off camera. You don't need to watch me sit here and do this. All right, so here's your completely randomized experiment. 200 campers randomly assigned to two groups, 100 and 100 campers, who are randomly assigned their treatments. All right, group 1 is either going to be high calcium or low calcium. Flip a coin. Of course, we're not comparing exam scores. We are comparing tooth strength. All right, that last little bit was the hardest to see. The question wasn't really clear, but it said they wanted to help keep teeth strong is the objective. So compare tooth strength seemed pretty good, but that question could have been better worded. All right, now we just need to make a matched pair, but it's time for class, so I'll have to do that later. All right, now for the matched pairs design that we're supposed to do now, matched pairs. Notice the first thing I did was I cut and pasted the completely randomized design because it's almost the same. All I need to do is add in a repetition of the treatment. I need to double up the treatment. So I'm just going to take this part, slide that over, okay? Okay. And I need to double up some treatments here.
Language arts training is in D105 at 3:45.
Okay, check it out. See, I accidentally doubled that too. Don't need that or this. Okay. Now, I'm not going to do high calcium, because that would be the same thing twice. That would be silly. So I'll just take these and I'll switch them up. All right. If a girl already did high calcium, then she's going to do low calcium. If she already did low calcium, then she's going to go high calcium. All right. So we'll just switch those up. Okay. Now, so that's the key to your matched pairs, is that each girl does both treatments. Okay, so that's basically it. Notice how everything else is the same. Now I'm just going to make one more small change here at the end. I can't just say compare tooth strength, because it's going to seem like I'm still comparing group 1 to group 2 like we did in the completely randomized design. So I need to add in something here to show that I'm comparing each subject with herself, the same subject. We're just comparing the high calcium of the same subject with the low calcium of the same subject. So I'm just going to modify this, and instead of just saying compare tooth strength, I'm going to say compare same camper tooth strength. Okay? And just like that, it becomes a matched pairs design. So again, notice I just cut and pasted the completely randomized design. All I had to do was add in the repetition of the treatment, so each girl gets both treatments. All right, I just had to reverse those so they weren't doing the same treatment twice. And then I had to mention same camper tooth strength to show that we're comparing Susie with Susie, high calcium, low calcium. All right, now what's the advantage of matched pairs design?
Just a reminder, teacher.
Well, one of the biggest challenges that we have when we design experiments is eliminating those lurking variables, where there's some sort of a variable that's going to affect the results even though we're not trying to measure it. All right, so if there's some sort of a difference in the subjects, then that's a problem. We want the two groups to be as similar as possible. But what could be more similar than yourself? So if you have the same person doing a treatment, and then you can see how that goes, and then you can have the same person do the other treatment, and see how that goes, that eliminates a lot of the lurking variables, all right, because the groups are identical. All right, and here I'm just writing that down. So because you're comparing the same subject with herself, you eliminate most of the lurking variables. We always want the experiment group and the control group to be as similar as possible. Well, when they're the same person, the experiment and the control are identical. So that's the advantage. All right, I think that's the end of this review. So that's the end of the video. I hope it was helpful. I will see you on the next video.